Okay, so let's come back to our class. So in the last hour, we have been further delve into the details of the max flow and the min cut problem. And basically, we have this idea of considering the residual graph. And having this residual graph, it is very natural that we consider we didn't totally abandon the gradient strategy, but actually we improved that. We follow the gradient strategy, but actually we consider this kind of augment algorithm on this residual graph. That basically we have this kind of forward edge and backward edge. And basically we denote the bottleneck basically for each path and for each flow we consider is bottleneck. And basically according to this is like a forward edge or a backward edge. Basically we correspondingly increase the function value consider the reverse direction of the edge, but that is an edge in the original graph, and we decrease the corresponding FE value. And basically we consider such kind of augment algorithm. And basically at the end of the last hour, we have this argument of the lemma that basically we are pretty sure that actually even using the augment algorithm here, we are actually still going to get a flow here that actually the capacity conditions and actually the conservation conditions, they are still actually going to be satisfied. Is there any question about this proof of the lemma? So I guess I was a little bit rushing in the last hour to prove this. So do you have any questions for this lemma? Okay, so if there's no question, I guess this finally goes to the algorithm that we are going to introduce. But this is still this is only like an augment algorithm. For like a specific path in this residual graph. I guess we need to really give a complete algorithm here for solving the max flow problem. So we say that finally we use augment to give an algorithm for max flow. So this max flow problem is actually this corresponding algorithm is actually originally proposed by Ford and Fulkerson. So we will just call this algorithm as the Ford-Fulkerson algorithm. So how does the Ford-Fulkerson algorithm look? So in general, for the max flow problem, the input is going to be the graph G here. And we are going to have designated a starting point S and actually the terminal point on the sink T here. And actually, it is also very important we have a capacity function on all of the edges here. So the Ford-Fulkerson algorithm, initially, it's just like, it's basically the gradient strategy that we are going to use here. So of course, initially we don't have anything, so we just initialize FE to be 0 for all E in G here. So where there is an ST path in the residual graph, so where there is still a ST path here, we just let P be a simple ST path. So, if you have a ST path, you can always make it to be simple. For instance, maybe your ST path looks like this. This is the S and T. You just, if there are some cycles along this, you just like ignore the cycles. You can just do like this. So, as long as you have a ST path, it is not difficult. You can actually find a corresponding simple path on this. So you just consider corresponding a simple path. Along this and actually for this. I should mention that this is a simple ST path in the residual graph. And after doing that, you have this F prime to be the augment actually of the PI. And actually update F to be F prime. And update the residual graph to be. So while you can still do that, while there is still an ST path in the residual graph, you just do this again and again until there is no ST path in the residual graph GF here. And in that case, you just return F. So this is basically the statement of the Ford-Fulkerson algorithm. So I guess after stating this algorithm, I mean, at least from my perspective, there are two immediate questions that we need to be careful with. I mean, in general, for an algorithm based on this while structure, it is always a question that when the algorithm is going to terminate. I think here we say a little bit more specific. So when the central while loop terminates. And the second question is that whether the flow, I mean, if it actually terminates, whether the flow return is a maximum flow. I mean, basically, the correctness of the algorithm. I mean, of course, another very natural question is the time complexity of this algorithm. And we will analyze it later. But these are like two very immediate questions that we should be very careful with. And I guess we should probably discuss them in detail here. So here, another very important assumption that we are actually going to make, which is actually important, is that all capacities are integers. So this assumption is actually quite important in the discussion below here. And in general, for the max flow, actually the mean cut problem, and actually a lot of applications of the max flow algorithms. So here we make the assumption that all capacities are integers. So after making this assumption, I guess an immediate lemma that we can easily see here is that at every step of the Ford-Fulkerson algorithm, the flow is actually always at everywhere going to keep integer values, the flow of values Fe, and the residual capacities in GF are all integers. So if we have the assumption that all capacities are integers, I mean, even in every step of the Ford-Fulkerson algorithm, I mean, this is still going to be kept. I guess this proof is actually also going to be quite intuitive. So it actually just works by induction. So it's just trivial at the beginning because we assume that all capacitors are integers. So at the beginning, it's definitely true. So, I mean, suppose we have run the while loop. Say for j minus 1 iterations. So if we have such kind of assumptions that basically, I mean, for the jth iteration, I mean, since all residuals are all residual capacities, yes, are integers, the value, basically this value, a bottleneck. I think because we are talking about a bottleneck here, and basically the bottleneck is the value that we basically augment each time. So basically the value of bottleneck df for augment, and will be an integer. And this is actually going to imply that f prime is still going to have integer values. And actually, so will the capacities in the residual. And say in the new residual graph. Let's try and okay, so any question about the the Ford-Fulkerson algorithm and actually the very first lemma, that even the assumption that all capacities are integers, we are going to know that even in every step of the Ford-Fulkerson algorithm, the flow values and the residual capacities are still going to be integers. So any questions for this? Okay, so if you have no question for this, I guess we are going to make some further discussion. I guess basically the fact that basically all the values here always keep to be integers is also going to be very important for us to make the discussion. So next thing that we can clearly see is that basically, I guess this is also something a little bit trivial, that actually the flow value strictly increases. When we apply augmentation. I guess this should also be a relatively straightforward. And in particular, I mean, we can clearly see that the value that we actually increase to the value of the flow is basically the value of the bottleneck, because that is the value that we actually are making through the corresponding flow here. So we make this a little bit more formal. So we say that actually, let F be a flow. F be a flow in G here. And we let P be a simple ST path in GF. Then basically, as I just mentioned, the value of the F prime here should be the value of F plus the bottleneck, PF. And actually, since we know, I mean, we are talking about the ST path in the residual graph, and we know that the corresponding bottleneck is actually PF is actually larger than 0, or we have F prime is larger than VF. So here, I think one observation that I think I would want to make a clarification here is that, and since a bottleneck PF is larger than 0, so let's actually go back to a little bit, I mean, at the part where we define the forward edge and the backward edge. So here for the forward edge and backward edge. So here, I mean, for instance, in the forward edge is corresponding definition. I mean, as long as we have an edge, its corresponding FE is actually a strictly smaller than CE here. So actually, I got messed up. I mean, let me actually also erase this C to make this to be the C bracket E. So let's go back to the definition of the forward edge and the backward edge here. So I mean, we have a forward edge as long as the FE is strictly smaller than CE here. Then basically we put a capacity. I mean, we put a corresponding forward edge in the residual graph with capacity of CE minus FE. We know this is actually some value strictly larger than 0. And similarly for the backward edge, I mean, as long as we have an edge whose function value is strictly larger than 0, we put the reverse edge with the same value, basically the FE, and we call this a backward edge. And actually this value is also strictly than 0. So this just suggests that all the edges in the residual graph, they must have strictly positive widths. There is no edge with 0 width in the residual graph. And actually, as long as you can find an ST path, I mean, as long as you can find an ST path, the bottleneck, I mean, since the weight of all the edges are strictly positive, the value of the bottleneck should also be positive. And that is why the argument here, we must have the value of F prime is larger than the value of BF. So this is an important observation that we make in the residual graph. So let's actually write a relatively concise proof. I guess it should be actually intuitive, but let's actually clarify a little bit details here. So recall the value of a flow is actually a VF equals to the summation E out of S. So this is the definition of the flow here. So we take a close look at this ST path here. So the first edge. So the first edge E of P must be an edge out of S in the residual graph. I mean, because we are talking about an ST path, I mean, in the residual graph. So it is just straightforward that the first edge of P is just like an edge going out of S here. And furthermore, since P is actually a simple, it does not visit S again. And actually, since S only has odd edges, E must be a forward edge. And after having that, I mean, we know that this E must be a forward edge. And I guess basically, we know that actually when we do this augmentation, that basically we increase the flow on E by this bottleneck value, by bottleneck PF, and do not change the flow. Change the flow on any other edges. Basically, because we basically need to be careful about this definition of E out of S. But in general, I mean, since E is the only edge that actually are leaving S here, so we are actually not changing the value of the flow on any other edge incident to S. So therefore, we know that VF prime equals to VF plus the bottleneck PF. And actually, this finishes the lemma, and we correspondingly know that the value is actually going to strictly increase. Okay, so any question about this lemma? I guess this should be relatively like intuitive. Okay, but this lemma is actually very important because this shows that actually by doing augmentation is that the value of the flow is going to strictly increase. And also very importantly, we have argued that the value of everything here must be an integer. So does the flow. I mean, the flow value should also be an integer. The increase of an integer should be at least 1. So this is actually a very important point here. So and actually, I mean, basically the increase, I mean, it is not increase each time we increase a little bit, and each time we increase by a value at least 1 here. So this is actually a very important thing that we want to keep remembering here. So actually, then we can denote basically a value which is C to be the summation of all the E out of S CE. So we denote this value to be C here. So basically the capacity of all the edges actually sum of the capacities of all the edges coming out of S here. So basically based on the lemma above, we have the following guarantee. So the guarantee is that we are going to have a clear time complexity bound on the Ford-Fulkerson algorithm. So clearly on the Ford-Fulkerson algorithm, exactly it is going to terminate in at most C iterations of let me take a look. I think, let me see. So for the max flow algorithm, talking about ST path. Oh, sorry. Let me take a look here. Sorry. I guess it should be just at most C iterations, because actually the C here is actually defines the summation of all the, the capacities of all the edges coming out of S. So each time we can actually increase at least, each time we actually increase at least value 1 of the corresponding flow value and the upper bound. The final upper bound, it just definitely cannot blow the value of C here, because actually this is the, the max flow should be actually at always actually going to be bounded by, I recall that we have this, lemma here. Basically the weak duality here. So the weak duality, basically taking the S as the set A here is just going to give you the fact that the flow value is actually going to be smaller than the summation of all the capacity of all the edges coming out of S here, which is actually going to be smaller than 30 in this case. So definitely we know that the flow value is the C here is a hard upper bound here. And actually each time we are going to increase it by at least 1 here. So we definitely know that the Ford-Fulkerson algorithm is actually going to terminate at most C iterations of the while loop. And actually we say that with total time OMC, total time complexity to be O of MC here. So this is basically the time complexity of the Ford-Fulkerson algorithm. So keep in mind that we have not analyzed the correctness of the Ford-Fulkerson algorithm. We have not proved that we actually output a max flow. But at least, based on the discussions above, we can clearly see that the Ford-Fulkerson algorithm actually going to terminate. And actually, it is going to terminate in time O of MC here. So this is basically the argument that we are going to make. Basically, after making this argument, let's then come to the correctness of the Ford-Fulkerson algorithm. So basically, as we just said, we are just saying here, so in each iteration, the value of the flow is increased by at least 1. And it has an upper bound of C due to a weak duality. We just implies that the number of iterations at both C here. So this is a very quick argument that we can actually very easily see by the discussions here. So I think now we just basically need to analyze the time complexity. So regarding time complexity, so the residual graph GF has at most 2m edges. So if the original graph has m edges, the residual graph has at most 2m edges. So it's basically in G gives rise at most 2 edges in GF. So this is a very straightforward observation that basically this residual graph should not be too large. And actually, having this observation, we know that basically in each iteration of the while loop, so each iteration of the while loop actually are to find an ST path. In GF, we can use BFS or DFS with the cost O of 2m plus m, but it's just O of m plus. And actually, furthermore, since we assume that each node has at least 1 edge. That's basically going to imply that m is actually at least n over 2. And basically, on this O of mn just equals to O of m, because m is basically at least has the same magnitude of n here. So basically, the cost is basically called O of m of finding an ST path. I mean, after that, after finding an ST path. After finding an ST path is basically the part where we run the argument. What is the cause of the argument? So basically, we want to keep in mind that the path here, P here we choose is actually a simple path. A simple path is going to have at most n-1 edges. So we are actually pretty sure that the argument is going to take time O of n, because P has at the most n vertices, and actually at the most n-1 edges. And actually, we can say that after that, we can do this like given the new flow F prime. I guess the remaining thing is that we need to update the corresponding residual graph. But to update the residual graph, we just need to take care of each of the forward edge and the backward edge. So, but this is not something very difficult. We say that we can build the new residual graph in OM just by going through all the edges in G. So all this discussion is just saying that the total cost in each iteration is just going to be O of m plus so this is the O of m here plus O of n, which is basically the complexity of actually going through the argument path, and actually another cost of O of m to reconstruct the residual graph. So basically, the overall cost is O of m, and the constant overhead here is at most 3 here. O of m here, and basically smaller than at most C iterations in total is going to give sure that the total time complexity is going to be O of MC here. Okay, so any question on the time complexity of Ford-Fulkerson algorithm? The key point is just that we have the while loops. And I think on the one hand, we want to bound the number of while loops. And on the other hand, we want to bound the cost inside each of the call of the while loop. So basically, we clearly see that the importance of the integer assumption here, that basically all the ways here is they are integers, is just going to imply that the bottleneck, basically this value increase each time is going to be at least 1 here. And actually, we know that the overall, the value of the Maxwell should be at most C here. Basically, this gives the upper bound about like the number of iterations is going to be at most C here. And basically, by looking at this clearly, it is not hard to figure out that basically the cost inside each iteration is going to be bounded by O of m here. And that actually is going to give the overall cost of O of m times C here. Okay, so basically this finishes the argument of the time complexity. Basically, this answers the first question that the algorithm is going to terminate. Actually, the time complexity is reasonably good with O of m times C here. So we see that this actually gives the time complexity in actually a promises the termination of the Ford. So I think in general, we want to prove that there's a Ford-Fulkerson. Not only it has a good writing time, but actually solve the problem that we want to solve, to actually solve the max flow problem. So this is definitely something we need to prove next. So basically we say, how about this correctness? So this is something that we need to prove now. Okay, so the main theorem about the correctness part is actually going to read as follows. Let me actually zoom in a little bit. So theorem is that a flow F is a max flow. If and only if, so recall that I write IFF to represent if and only if there are no augmenting paths. Therefore, just this is like an if and only if here. So therefore, for the Fulkerson, outputs a max flow. The second point we want to argue is that the value of the max flow is actually equal to the value of the mean cut. So this is a very important theorem that we are going to prove, because after all, I mean, we have been talking about for more than 2 hours about like the max flow problem, the mean cut problem, and this idea. I mean, based on this greedy algorithm, and then after that we have this augment idea, and basically finally going to this for the Fulkerson algorithm. I mean, this is basically the theorem that we want, and actually we have analyzed the time complexity of the Ford-Fulkerson algorithm, and basically after we finish proving the theorem, I guess that is basically the rest of today. I think this is like for around 20 minutes. I guess this is basically what we need to finish, and we try to give a proof here. Okay, so let's do that. So here, I mean, there are some, I mean, for instance, for the first point, this is like a if and only if condition. So this is a little bit, I mean, maybe you want to think about like a good strategy that in general, maybe we want to simultaneously argue for point 1, point 2 here. So we not only want to prove that a flow is a max flow if and only if there are no augmenting paths, but maybe along this way, we can actually give like a constructive way, actually a construction for the mean cut here. So basically here, I mean, looking at all these points, we do the claim as follows. So we prove both claims. Actually by this. So basically by showing the equivalence of following claims. So we have 3 claims here. So the first claim is that there exists a cut AB such that, I mean, given a certain flow here, that the value of VF actually equals to the capacity between A and B. And the second point is that your current flow is a max flow. And the third claims that is going to be there is no augment in path with So we are basically going to show the equivalence of these 3 claims. And actually, after showing the equivalence of the 3 claims here, you can clearly see that basically the equivalence of the 1, 2, and 3 here is actually going to give you the promise of both arguments. Because basically we have the argument 2 here, the value of the max flow is actually going to equal the value of the mean cut. Because we have figured out a flow that actually satisfies this claim. Because basically the main point is that the output of for the Fulkerson algorithm is going to satisfy the third claim that there is no augmenting path with respect to it. Basically, due to all these equivalences that we are, if it were true, I mean, we are going to prove it right now that actually 1, 2, and 3 here, they're equal with each other. We are then going to, based on the fact that the Ford-Fulkerson algorithm satisfies the condition 3 here, then basically the condition 1, the claim 3 here, then basically after that, the claim 1 and claim 2, they are actually also a correct claim. So basically, we then promise that the flow F here is actually a max flow, and then correspondingly, there exists such a kind of a cut such that the VF is actually going to equal to the cap of A and B here. So the remaining thing is that we need to show the equivalence of these 3 claims. And actually, to show the equivalence, it's just like surfaces that we do like in kind of like a cycle argument. So basically we do 1 imply 2, 2 imply 3, and 3 imply 1. So basically, as long as we can finish the whole logic, we show that having 1 imply having 2, having 2 imply having 3, having 3 imply having 1, we are basically finished. So let's do this gradually. So basically for 1, 2, 2, if there is a cut such that VF equals to cap AB, then the flow F is a max flow. And this is just the weak duality lemma. So 1 to 2 is probably the most trivial part of this proof here. So then we go to the 2 to 3. That the flow F is a max flow is going to imply that there is no augmenting path with respect to F. So this is also quite straightforward. This can be easily seen by a contradiction argument. So assume that 2 does not imply 3 here. So assume that F is actually a max flow, but there is an augmenting path here. So if not, and there is an augmenting path. We can improve F by extending flow along that path. Along that path, and this contradicts with F in the mix. So then the remaining thing is going to, we have a 3 imply 1 here. So this part is a little bit sophisticated. So before introducing that, is there any question about the theorem statement and the idea that we are going to show the equivalence of the 3 claims here and 1 to 2 and 2 to 3 before we show 3 to 1? Any quick questions? Okay, so now we are basically going to show that as long as there is no augmenting path with respect to F here, there actually exists a cut AB such that the value of F is actually going to equal to the capacity between A and B. So we do this. So now we have a flow F with no augmenting path. So basically having the fact of no augmenting path, and we want to basically prove that there exists a cut such that the value, the cut value actually equals to the value of the F here. Basically, the idea is that we want to use this flow to basically utilize the structure of the flow to define such kind of cut. Especially we want to figure out hopefully we want to figure out some set A and B here that maybe if we look this closely, and as long as we have no augmenting path, the cut value must equal to the flow value, and basically everything just finishes. So basically, this is the observation here, and actually, the A here that we are going to select here is that let A be the set of vertices reachable from S in a regional graph. In a residual graph. In a residual graph. So we consider the set of all vertices reachable from S in the residual graph. And we are going to argue that the cut value between this A and the V over A here. I mean, of course, I mean, basically having this definition, I mean, reachable from S, of course, S is going to be in A here. And we denote B equals to V over A. We are basically going to show that the cap of A and B is cap between A and B actually equals to the flow value of F. So basically we denote B equals to V over A here. So since F has no augmenting path, clearly T is not in A. Otherwise, I mean, T is in A, this just by the definition of A, because the set of vertices is reachable from S in the residual graph. I mean, if T is reachable from S here, and actually T is in A here, this gives you a ST path. So because there is no augmenting path here, we are pretty sure that T is not in A here. And just hence, T is actually in B. So there are some furthermore fact. So for in the original graph, for all E out of A, we know FE plus equals to. Why is this? This is the case. So in the original graph, for all E out of A, we are going to have F equals to C. So the reason is that for E out of A, I mean, when we in general talk about E out of A, I mean, in general, I mean, E is basically going from A to B here. I mean, here, if FE is actually smaller than CE here, just by the definition of the residual graph, we are actually going to have this edge E here, actually with corresponding capacity CE minus FE here. So we know that actually FE is always smaller than CE here due to the capacity constraint. But if it is the point where the strict FE is strictly smaller than CE here, it just does not satisfy the definition of A here, because for the definition of A here, we are talking about the set of vertices, all the vertices reachable from S here. I mean, if FE is actually smaller than C, you should have actually put this point. I mean, this point should be put in A here, should not be in B here. So it does not actually make sense. So these are very important fact. I mean, actually taking this set A to be a set of all the vertices reachable from S, this is very important. And actually taking the set A here is actually going to have this kind of observation. And actually not only having this, and actually for all E into A here, we are going to have FE equals to 0. Otherwise, there should be a backward edge here that actually leaving A to some vertices in B here, but this also is going to contradict with the definition that A is the set of all vertices reachable from S in the residual graph. So this is actually going to be a critical here, and actually recall what we have proved here, that VF is actually taking some arbitrary set. You are going to have this relation that E out of A FE minus the summation of E into A FE. We know that this is true for arbitrary subset A here, and we take the A here to be the A, we basically we take it to be this A. So, I mean, we clearly see that basically this furthermore effects, they are really important. Basically, we plug this here. We're actually going to have the summation. The first summation is going to be E out of A. For all the edges E out of A here, we know FE equals to C. And for the other part, for all the E into A here, we know FE equals to 0. So we can simply say that this equals to this minus 0. And this just equals to the capacity of A. And this finishes the proof. And I guess here, I mean, for this part, I mean, if you not fully understand this, I guess there are some comments here. So maybe let me just, I mean, to get everything, I mean, just like say this again. So for E, U out of A actually goes from U belongs to A and V belongs to B, but V not in A, not connected. Yes. in the residual graph. And this is actually going to give no forward edge. Backward. Goes to C. And on the other hand, similarly, I mean, this is basically, I mean, let's say this is 1. Maybe let me not say 1 here. Maybe let's say this is A and this is B here. So the A actually follows from this, and actually B follows from the fact that E goes to VU here now into A. And goes from B to A, but actually V is not in A, not connected to S in the residual graph. And actually, this just implies that no backward edge. And this at this edge, it is going to be a fully forward, so that FE actually equals to. So that is basically like a further explanation of A and B here in like a proof. But the intuition, as I just mentioned, is that we are actually very carefully utilizing the fact that the A here, the set A here to be the set of all vertices reachable from S in the residual group. Actually utilizing this basically for this equality here, we further utilize the structure that actually for all the E out of A here, if E equals to C, and for all the E into A here, if E equals to 0. And this, just for this very specific case, we know that if VF is actually going to equal to the capacity between A and B here. And basically this finishes the most sophisticated part from 3 to 1 here, and basically finishes the whole part, basically the correctness of the focus. So any question about this proof of the correctness of the Ford-Fulkerson algorithm? So I guess I have like about 3 minutes. So let's make a very quick final argument here. So the final argument here is a corollary. So the corollary we are going to give is actually is basically a few observations. Is that basically the Ford-Fulkerson algorithm actually it outputs the value of max flow mean cut in time O of MC. It's just like you can just store this value. I mean, because in this Ford-Fulkerson algorithm, I mean, it's basically each time you are just updating like this. So you just store the value of the bottleneck. I mean, each time you just have a register there, and each time you're actually finding augmenting path and actually doing the augment, you just like add the corresponding bottleneck value into that, and then basically, finally your algorithm is able to output the value of the maximum flow mean cut in time O of MC here. So the second comment we are going to have is that after running for the Fulkerson, it basically gives a mean cut in OM additional time. So why is this the case? So this is basically the A in the above proof. And actually, we just need to run a BFS or DFS from S to determine A. The third observation is actually going to be very important. We are actually going to use this next class. This is called the inter-reality theorem. So basically, there exists a max flow such that FE for all E in E is an integer. If all the capacity is an integer. Okay, so basically this finishes the arguments of the Ford-Fulkerson algorithm that I mean some additional points that in general we can actually output the value of the max flow mean cut in time O of MC, and actually after that we can, I mean for the mean cut we can just output the mean cut. It's just, I mean, after we output this graph, this flow where there is no augmenting path, we just run the BFS or DFS from S in the residual graph to determine the set A here. And after that, I mean, from all this argument, I mean, also another very important thing is that actually there exists a max flow such that the flow value, and actually, I mean, for all the edges, I mean, is actually an integer if the input, I mean, all the capacities are integers. So basically this finally finishes the argument of the max flow mean cut problem. We give an efficient algorithm to solve the problem. And basically for the next class, we are going to, I mean, find some applications of this. I mean, today, I mean, for this problems, I mean, for the max cut, sorry, for the mean cut and max flow, it's really like a graph problem. But actually, we will see the power of the network flow algorithm, for instance, like using the Ford-Fulkerson algorithm and a black box, it can be applied to many different scenarios. And this is going to be something we are going to introduce in the next class. Okay, thank you for your time and see you next week.